X-rays are pretty incredible. They're this medical marvel that lets us literally see inside the human body, no scalpel required. But that amazing power, it's a real double-edged sword. There's a hidden risk we have to be super careful with. So, what's really going on every time someone gets an X-ray? Okay, just look at these two images. On the left, you've got this crystal clear chest X-ray. That's the kind of image that can save a life. But on the right, it's a foggy mess. It could be hiding something really dangerous. Now, they're both X-rays of the same thing. So how does one end up a lifesaver and the other a total liability? And the difference isn't just, oh, that's a bad picture. It's way deeper than that. It's this delicate dance between physics, biology, and some seriously clever technology. So let's dive in and uncover the story behind every single one of these images. All right, first things first, let's pull back the curtain a bit. Where do these incredible invisible beams even come from? Well, it all starts inside this thing called an X-ray tube. The easiest way to think about X-rays is like light, but just with way more energy. And they're born right here, inside this vacuum-sealed tube that has two key parts, a negative end called a cathode and a positive end, the anode. And this is how it works step by step. First, a current heats up a tiny filament until it gets so hot that electrons literally start boiling off its surface. That process has a fancy name, thermionic emission. Then a huge voltage difference, like a giant slingshot, launches these electrons across the vacuum. They slam into a metal target at incredible speed, and that collision is just immense. Get this, 99% of all that energy just turns into heat, but that last critical 1%, that is released as X-rays. So that tiny 1% is where all the magic happens, but it's also where the danger lies. The very thing that makes X-rays so useful, their power, is exactly what makes them potentially harmful. And that right there is the central conflict of this whole story. The key word we need to understand is ionizing. It basically means that X-rays pack enough of a punch to knock electrons right out of the atoms in our cells. And when that happens, it can mess with all sorts of vital processes, like how our cells divide. That's where the direct risk to our health comes from. Okay, so to really get a handle on this risk, let's set a baseline. We're all getting zapped with a little bit of radiation every single day. It's totally natural. It comes from the ground, the air, even space. So the average person in the UK gets about 2.2 millisieverts, or MSV, a year, just from, living on Earth. Remember that number, 2.2. Now, hold that thought. A single CT scan of your abdomen, that can deliver a dose of 10 millisieverts. Yeah, that is a massive jump from what we get from nature in a whole year. Let me put that another way for you. One single CT scan is the same as getting 4.5 years of natural background radiation all at once. And that right there is exactly why every single scan has to be clinically justified. The doctor has to be sure that the benefit of seeing what's inside you is way bigger than the risk. And we're not just talking about some abstract long-term risk here. Really high doses can cause immediate, visible damage, like the severe radiation burns you see in this picture. The biological effects are absolutely real, and they are completely dependent on the dose. Okay, so we've got a powerful tool with a known risk. But believe it or not, there's another villain in this story. It's kind of this unseen saboteur that makes everything more complicated. It messes up our images and even adds to the danger. And its name is scatter. The main type of scatter we're worried about is called Compton Scatter. The best way to picture it is like a game of pool. The incoming X-ray photon is your cue ball. When it smacks into an electron in your body, it sends that electron flying off. That's the ionization we talked about. But the cue ball, the photon itself, it doesn't just stop. It ricochets off in a totally new direction, and it loses some of its energy in the process. Now, during an X-ray, this isn't happening just once. It's happening millions and millions of times. The patient's body literally becomes a new source of radiation, spraying these weaker, scattered X-rays out in every possible direction. Kind of crazy, right? And this scatter radiation, it's a real triple threat. First, it adds to the patient's overall dose, because those scattered rays can get absorbed somewhere else in the body. Second, it's the #1 source of radiation exposure for the medical staff in the room. And third, remember that foggy picture from the beginning? That's what scatter does. It hits the detector from all these random angles and just ruins the image quality. So you've got this super high energy beam you're trying to control, plus this chaotic cloud of scatter flying everywhere. How on earth do medical pros tame all that wild energy to get a clear picture and keep everyone safe? Well, it all boils down to a few core principles of protection. Think of these as the 3 pillars of radiation safety. First, justification. We've touched on this. Is the exam actually necessary? Second, optimization. That means using every tool and trick in the book to lower the dose. And third, ALARA. It's a guiding philosophy, an acronym that stands for as low as reasonably achievable. The whole point isn't just to stay below some legal limit, it's to cut out every last bit of unnecessary exposure. And for the staff in the room, one of the most powerful allies is a basic law of physics, the inverse square law. All it means is that if you double your distance from the radiation source, your exposure drops to just 1/4 of what it was. That's huge. Just taking one big step back can make a massive difference. But, and this is where it gets really interesting, it's not always that simple. A study in the Health Physics Journal actually found that in the real world, just stepping back doesn't reduce the dose quite as much as the textbook law predicts. And why is that? Well, because a human body isn't a perfect sphere. It's a complex, irregular shape that reflects and scatters radiation in all sorts of unpredictable ways. It's a great reminder that the real world is always a bit messier than the physics lab. So if we can't completely escape the scatter, how do we fight back? How do we defeat it where it matters most, on the final image? This brings us to the final act of our story, the amazing tech designed specifically to conquer that unseen saboteur. I mean, just look at the difference here. It's night and day. On the left, you've got that washed out, foggy image, totally ruined by scatter. On the right, it's the exact same anatomy, but it's sharp, it's clear, it's full of diagnostic detail. And this incredible transformation is all thanks to a simple device that's been a cornerstone of radiology for more than 100 years. And here it is, the hero of our story, the radiographic grid. It was invented way back in 1913, and its design is just brilliantly simple. It's basically a plate with these super thin strips of lead inside, and you place it between the patient and the detector. Now, the good X-rays, the ones traveling in a straight line from the source, they pass right through and make the image. But all those pesky scatter photons, coming in at an angle, they get caught by the lead strips. It's honestly like a set of Venetian blinds, just filtering out all that unwanted, stray light. But of course, even here, there's a trade-off. It's never that easy, is it? Grids come in different ratios, which is just a way of describing how tall the lead strips are compared to the spaces between them. A high-ratio grid does an amazing job cleaning up scatter. You get a beautiful, crisp image. The catch? Because it's so good at blocking things, it also blocks some of the useful X-rays. So to get a good picture, you actually have to increase the initial radiation dose to the patient. It's this constant, delicate balancing act. And really, that brings us to the final thought here. The whole story of the X-ray is the story of that balance. It's this constant push for clearer, more detailed images versus the constant pull of patient safety. Every single step, from managing the radiation itself to defeating scatter, is a calculated decision. And as our technology gets more and more powerful, allowing us to see inside the human body in ways we never dreamed